Good afternoon. I'm Donna Rizzo. I'm a professor in the College of Engineering and Mathematical Sciences and a Gunn Fellow. And what does that title mean? Easiest way for me to explain to you is with an example, a groundwater contamination problem that started actually my PhD work. This was out at Lawrence Livermore National Lab, located 40 miles east of San Francisco. You're looking down at a plan view of their 2D groundwater flow and transport model. All DO sites, facilities, and groundwater are contaminated. It only becomes a problem when the contamination moves off-site. I turned it into a 3D model, and you can the only thing I really want you to take away from this particular slide is that when I represent a little red dot here, it represents a single design to clean up a groundwater problem. So that particular node represents perhaps wells that are pumping water out of the ground, treating it on site, re-injecting it back into the ground. And from an engineering perspective, I care less about learning about the physics of these process-based models. I usually take somebody else's model and I use it to project things into the future, perhaps a design so that you can come up with a solution. In this particular case, I'm wrapping a design. That particular design, one design, has a cost associated with it located along the horizontal axis. We'd obviously like to minimize costs if we could. So optimization tools, I consider them wrappers, which I would wrap around other people's physics-based models. And in this particular case, you can pretty much clean up anything you want if you have enough money. But one of the things that makes it more fun for me is in this particular case, EPA said, well, clean up all the contamination to less than 5 parts per billion in 30 years. Well, we gave Livermore back a bunch of solutions that must have been pretty good because they came back with another constraint. Constraint said, okay, you know what, could you do the same thing again, but this time do it with only putting in 28 wells over the 30-year period. That's a financial constraint. So I knew I was onto something. So we gave them another set of solutions. They came back to me and said, okay, well, could you do it again, but only pump 18 of the wells at any one time because we can't treat more water than that on site and re-inject it. So we ran the simulations again and gave them back another solution, and I thought, well, this is a little confusing. If I can only put 28 wells in over the 30 years, and I can only pump 18 of them at any one time, we have a problem. So we developed this thing called multiple management periods. Every 5 years, I'm allowed to change the well configurations. So in this particular scenario, I would put in 28 wells perhaps over the whole 30-year period, but we'd only pump 18 of them, maximum of 18 of them at any one particular time. All right. That unfortunately leads to a lot of computational problems. One of which being if you just, every single one of those crosshairs on that grid could be a potential well location. If you just took it 50 of them that are really good locations and looked at all possible combinations of 28, you'd have to exhaustively search 10 to the 14 different solutions to find the optimal answer. If you take those same 50 locations and you allow every combination of 1, 2, 3, all the way up to 28, you end up with 10 to the 15. If you then add the management periods that I did, you end up with 10 to the 61. That's more than the number of atoms in the universe. So you need tools to help you find these kinds of solutions. In this particular case, we're trying to minimize an objective function that involves multiple stakeholders. So everybody has a different opinion, and the one thing you can be assured of is that with multiple stakeholders, there's no such thing as an optimal solution. Anyway, this particular cost function, you usually have some actual real dollar costs associated with your design, and the latter side of this equation is all the other things we care about in society. So if I really wanted to minimize this mathematical expression, I should probably do nothing would be the cheapest cost. But that's not going to satisfy the other constraints that we care about. So these two sides of this equation are diametrically opposed to each other. We just introduce a penalty factor, and if up front someone could tell me what design they would use, I can pretty much tell them how much they should pay for clean water. Okay, in this particular case, think of EPA is the horizontal axis. The lab is the horizontal axis. They want me to minimize costs. The vertical axis are the people drinking the water. They want me to minimize risk. I'm going to allow the computer to basically do the work for me. And in this particular case, I'm just going to add one more stakeholder. Now that vertical axis is, oh my God, okay, sorry. We're looking at a huge number of design optimizations. I'm looking for a global minimum. I'm using something in this particular case called simulated annealing. Now we use things called genetic algorithms. And this is my last slide. We present these results to multiple stakeholders and then use these as a ways of conflict resolution.